2, or or excuse me, 5 square root of 2 over 2, as it's written in CalChat. But
Uh, okay.
I'm not getting the y. I don't know how to plug it. I guess I'm plugging it in wrong somewhere.
So let me actually kind of work my way through this. This is problem 25 on page 225. So we've got a semicircle that has equation y equals the square root of 25 minus x squared. And we're fitting a rectangle under that. And let's call, kind of like they do, let's call this point right here xy. Let's see if we can set this up really in the context of the optimization problems. So the variables have already been set up for us. Our objective is to maximize area. Oops. You still there?
Yes, sir.
Okay, I got a error message on my screen. And the area of a rectangle is base times height. Now, this x right here is just the distance from the y-axis to this point. So the entire base of the rectangle is going to be 2x, and the height is given by the y-coordinate at this point. So that's 2xy. And the constraint for this problem is going to be that this corner has to lie on the semicircle. So the constraint is that y is the square root of 25 minus x squared. And then after we've written down the objective function and the constraint, then we substitute the constraint into the objective function. So I'm going to replace the y with the square root. So I get 2x times the square root of 25 minus x squared. Is this kind of looking like the way you were doing it?
Yes, sir.
Great. Since this only has one variable in it, I'm going to call that a of x. And then we'll calculate the derivative. So this is going to be a little bit messy. Let's write this as 2x times 25 minus x squared raised to the 1/2 power. Taking the derivative a prime of x is equal to 2 times that square root, 25 minus x squared to the 1/2, plus 2x times, I'm going to have to differentiate this using the chain rule. 1/2 times 25 minus x squared to the negative 1/2 times the derivative of the inside, which is 2x. So simplifying a little bit, that's twice the square root of 25 minus x squared.
So would it be
Plus,
minus 2x?
oh, it sure is. Thank you. So this is a minus then. These twos cancel, and I have a minus 2x squared over the square root of 25 minus x squared. So I'm going to multiply this first one by square root of 25 minus x squared over itself to get a common denominator. Ew, that's coming out terrible. Whoa. So down here in the denominator, I have the square root of 25 minus x squared. And on top, I have twice 25 minus x squared minus another 2x squared. So that's 50 minus 2x squared minus 2x squared. So that's 50 minus 4x squared over the square root of 25 minus x squared. And then I want to find the critical numbers of that, which will be the places where this is either 0 or undefined. Now, the place that's undefined is when x equals 5. But if x equals 5, then that means my rectangle is flat. So that has area 0, so that's definitely not going to be my maximum area. So let's find out the places where this is equal to 0. So I'm going to set it equal to 0, which is the same as setting the numerator equal to 0. So that means that 4x squared is 50. So x squared is 50 over 4. So x is going to be plus or minus the square root of 50 over 4, which is twice the square root, 5 times the square root of 2 over 2. And is that the answer you told me that you had gotten?
Yes, sir.
Somewhere. Once you have one of the components, the way that you get the other one is by plugging back into the constraint. So the y-coordinate is going to be the square root of 25 minus x squared. But x squared is 50 over 4. So underneath, getting a common denominator, that's 4. So that's 100 minus 50, which is 50 over 4. So that gives me, once again, 5 square root of 2 over 2. So x and y are the same. So when it comes back to telling what the dimensions of the original rectangle are, the base of the rectangle is 2x. So 2x is the same as 5 root 2. And the height is y, which is 5 root 2 over 2. So those are the dimensions of the rectangle that have the biggest area. And if I wanted to know the area, I would just multiply those guys together, which I guess is 25. Hi to all the Cal 3 students who just showed up. I'll be with you in just a second. Is that matching what you're seeing in Calc Chat?
Yeah, in CalChat, yeah, sure. It's not matching what I see on my paper, though.
Okay. Does it make sense, though?
Oh, yes, it does. I met someone, I have to find out where. I got the X, and so when I plugged it back into Y, I got, I think I just made a multiplication error somewhere. I'll find it.
Could be.
Yeah. 1 second.
Okay, real quick on the Cal 3 students, you guys are going to be uploading your bonus points in about 10 minutes or less. So do you have any quick questions about hints that you need? Or have you already uploaded it? You're good to go. If you're wondering about how to talk to me, you can either turn the microphone on, or if you click on that little, on my screen, it's a purple arrow in the lower right-hand side. If you click on that, it's a possibility of chat, that first little talking bubble window. You can click on that and send me a message.
Professor.
Yeah.
Okay, so I had a few questions here. As far as the exam on Thursday, I'm not sure if you mentioned like how it's going to work. but how's that going to work?
Yeah, so the exam's going to open up about 30 minutes before our regular class time, and it'll be opening up on Blackboard. So if you've been looking at the week 10 study plan, there's going to be one other item available there at, let's see, our class normally starts at what time? 11:45. So at 11:15, that will be opening up, and the exam will be there for you to download, or you can just look at it on screen. And you'll take it, and my expectation is going to be that you'll have the same resources available as if you're in class. So you'll have a scientific calculator, but notebooks, notes, apps, and so forth. And 2 hours later, actually, when class ends, you'll still have an extra 25 minutes to scan it and upload it back to Blackboard. So for us, that means that you'll be starting at 11:15, 11:45, 12:40, 12:35, 2 o'clock. 2 o'clock, the exam will close. If I'm getting any of these numbers wrong, if you look in that week 10 study plan, there's a fairly big bullet item that gives you the exact times that the exam is going to open and close. But the idea is you're just going to download it, take it at home on your paper, then scan it and upload it before the deadline.
Okay. Is it going to be is everybody going to be online? Is everybody going to get online and then like have like a FaceTime thing going on while it's going on? You just download it and just take it.
You'd better not. I just want you to log into Blackboard and just individually take the test and then upload it again. You'll just be working on your own.
Okay. So next question, I guess, before I forget, you said that we have 10 minutes before the. I thought was it the relay questions? I thought they were due from what I read at the end of the day today.
I think you got them backwards. The relay's due at 11:45. Your homework is due at the end of the day today.
Okay. All right. Well, okay, and the so the homework, I mean, is a lot to take pictures of. Because I was just going to take pictures of all. Normally what I do is I'll take pictures of all of it, put it on a Word document, and then upload that Word document so it's all in one place. Is that necessary, or do you want to just take a picture of this?
I can't see what you're holding. I don't think you have your camera on, but how many pages are we talking about?
Oh, let me see.
Dozens and dozens?
2, 3, 4, 5, 6, 7, 8, 9. Okay, so it's only 9. It's actually not that bad. But
yeah, go ahead and do that. One thing I'd like you to at least try doing is to see if you can find an app on your phone that allows you to take pictures that'll convert it into a PDF. Because when you upload PDFs to Blackboard, I can grade them on screen. And I want to try to grade everything on screen.
Okay.
And that's the way I'd like you to upload the test as well, is I'd like you to scan it, preferably either with an actual scanner or using some good app on your phone that lets you upload it as a clear PDF.
Okay. Okay. And so, I mean, but if I were to take like a really clear picture and just put it onto a Word document, would that work too? I mean, I'm going to look for something like that, but.
Yeah, if you take a picture and put it in a Word document, I think you could still save that document as a PDF and upload it in PDF format.
Right. Okay.
That's just putting some extra steps in there. But I'm giving you an extra 30 minutes before and an extra 25 minutes after the exam. So that should be enough extra time for you to go through whatever steps.
Okay. All right. Sounds good. I appreciate it. Thank you.
In about 5 minutes, I'll be glad to answer specific questions on the review. I can actually work problems out.
Okay.
I have a non-review question.
What's that?
So back to the book on 15.2, number 17.
Okay, heading on. You guys hang on for just 1 second. I'm going to mute my Okay, sorry about that. I'm back. It was 15.2. Which one, Jason?
Looks like 17.
Got it. So we're trying to parameterize that that curve that's made up of 3 line segments.
Yeah, and so they give us the curve shown in the graph, and then they want us to evaluate the integral. How do you say that, by the way? The integral symbol with the C at the bottom. How do you
You
say
say
that?
the integral along the curve C.
Okay, so they give us that. And when we're doing this, it looks like we've done our integrals from the way it's solved. I was just kind of wondering why is the integral, they always have it where t is between 0 and 1 and not like 0 to 1 and then 1 to b and then b to c and so on. Like on all 3 curves, it looks like it's t is from 0 to 1. Yeah,
Yeah,
curve 1 you
I
do
would
from 0 to 1, curve 2 you do from 0
I
to
would
1.
do it from 0 to 1, just because of the specific curve that we're working with. Let me give you another similar example where I wouldn't necessarily go from 0 to 1. Let's see if I can draw it. Let's say that the curve looked like this. Let's say that it started at 0, 0. It went along the y-axis to the point 0, 3. That's supposed to be a 3, 0. And then it went directly upward to 0, 3, 5. Let's just do those 2 parts. So we'll make this C1 and this C2. So if I wanted to parameterize C1, by the way, if you're just coming in, this is similar to problem 17 on page 1065. C1 is something which is along the y-axis, which means that x and z are 0. So I said x equal to 0 and z equal to 0, and I'd let y equal t, and I would be starting with y equals 0, so that's t equals 0, and I'd stop with t equals 3. So I'd let t go from 0 to 3 on that one. So sigma 1 would be of the form 0, t, 0, with this restriction on t. And for C2, I'm going vertically so that the only thing changing is the z coordinate. So all along that curve, x is equal to 0. Sorry, my pen's not being very responsive. Y is equal to 3 on that entire segment, but z is changing. So I'd let z equal to t. And I'd want to start out here, which has a t coordinate of 0. So it'd be starting at 0 and stopping up here at 5. So for that second part, I'd have t going from 0 to 5. So I think that in the book where they're just going from 0 to 1, that could just be because all of their endpoints have coordinates 0 and 1. Does that make sense?
Yeah, so I was also wondering how each function lined up with the graph. And so I think what I'm seeing is that when you're on curve 2, the y is considered fixed, it's a constant, it's always 3, x is a constant, it's always 0, and z is changing. Because on 17, their parameterization for curve 2, curve 2 starts at x equals 1, y is 0, and z is 0, and it runs upward to x is 1, y is still 0, but z is now up 1.
Mm-hmm.
And there you have I plus tk. Okay, so I see that the I in that case is always 1. It's a constant, and tk is variable. So it moves from 0 to, it's the variable that moves from 0 to 1.
That's right.
And in your case, in the one you've done, the variable moves from 0 to 3 in the first curve. Everything else is constant. The variable moves from 0 to 5 in the second curve, and everything else is constant.
So one thing that's different from what you typically saw when I was lecturing over this is they're writing something like, oh man, I'm so sad that this is not cooperating better. They're writing something like I plus tk. Maybe it's because my palms are getting sweaty.
Do you have a stylus? Is that what you're writing with? That's not good.
Sorry about that. You guys still there?
Yep.
Yeah. I'm using a stylus, but it seemed to work better when my palms were less sweating. Let's see. So what they're writing as I plus tk is what I would be writing as 1, 0, t.
Mm-hmm.
So in other words, x equals 1, y equals 0, z equals t.
Yeah.
Okay, so greetings to everybody who's coming in after turning in your relay. I'll be glad to answer questions out of the textbook or off the relay, or just general questions about the exam. You can either turn your microphone on and ask the question, or you can send me a message through chat. You can get to that using the little purple arrow at the lower right side of the screen, and then clicking on the chat bubble. How did the relay go?
I didn't actually do it. I mean, I tried to look over it, but I'm so far behind that. Like maybe by the end of I'm hoping by the end of today I could do the whole thing easy breezy. But as of right now, I'm like, I'm gonna have to do my best without bonus.
Yeah, that's a good plan. Remember that the answers are online, although unfortunately on the one that I printed out, it's hard to read the answers to 2 and 4. I'll go back and check on that and see whether that's just mine or something that I can fix to make sure y'all can read it.
2 and 4.
Yep.
2.
Can you read the answers to 2A and B and to number 4?
Is it just the PDF that has the answer, or is it supposed to have the whole solution worked out?
It just has the answers. It's on page 2.
Yeah, it looks like for 2A is x plus y plus z, and 2B is a vector 1 minus y, comma 1 minus z, comma 1 minus x.
Awesome. I cannot read that on the one that I printed out.
Oh, it's super clear on this.
Great.
And what was the other one that you thought wasn't clear?
Number 4. Can you read the
Oh, yeah. The very top of the number 2 is kind of cut off. You can tell it's 2x plus y plus 2z equals 10, but the very top pixels are cut off.
Yeah. What happened is for number 3, I pasted in a picture, and it looks like the edges of the picture might have covered up part of the answer.
Mm-hmm. It's legible.
Yeah, if y'all can read it, that's cool. One comment, I have not really started grading the submissions that folks have done for the bonus points. Some people turned them in last night. One thing that I am going to do is go through and just make sure that I can read them all. And I'm going to let you know, like if whatever you're sending is blurry, so that you can maybe find a better app or be more careful in taking pictures when you upload the test and the homework later today. I did notice a mistake that one person made on question 1, which is on the directional derivative. And that student wrote the answer, claimed that a vector was the answer. But remember that a directional derivative gives you a number, and that you'll be dotting the gradient with a unit vector to get that number. So when you carry out that dot product, looks like the answer should be 3. So if you still got yours handy, you might want to just look at the answer that you submitted for problem number 1 and make sure that you got a number as your answer and not a vector.
So to do number 1, you have this f of x, y, z, and so you turn it into a vector by doing, like, the x component is the partial of f with respect to x, the y is the partial y with and so forth, and then you dot that vector with the given vector 3, 6, -2.
Close. Remember, you have to take that given vector and make it a unit vector by dividing it by its length.
Oh.
So you take the gradient of f, like you described, and then substitute in p. So the gradient of f, I'll write it. You take the gradient of f and substitute in p, and then that's going to give you a 3-dimensional vector with just numbers in it. And then you'll dot it with the unit vector in the direction of v. So you have to take the vector v and divide it by its length. And the answer is going to end up being a number.
And on the test, is this type of question going to be like this, where we're pretty well given that, or is it going to be more like you're going to have to do some work to find what the unit vector, not the unit vector, you're going to have to do some work to find what the vector is so that you can find the unit vector. You may have to do some work to find out what the function is so that you can find the gradient of the function. Like, you could make this pretty complicated if you wanted to, or if this is, I think, more straightforward, where we're just given what we need and we just have to put it in.
The worst that you would have is I might, instead of giving you the vector v, is I could tell you that it was the vector pq, where p was the point, I'm just making this up, 1, 0, 3, and q is 2, 1, 4. So if instead of giving you the vector v, I just said it was the vector from p to q, then you would have to use the fact that you find pq by taking the terminal point minus the initial point. So in this example, that would be 1, 1, 1. Does that make sense, Jason?
Yeah.
So
okay.
You should expect that the corresponding problem on the test will be pretty similar to that. In fact, if y'all haven't noticed, you should expect that the exam is going to look a good bit like this relay does. The questions are going to be phrased in a similar way.
Can you do number 8, the Lagrange multiplier one?
Sure, let's look at that. So here we're working with a function of 2 variables. F of x and y is 5x plus xy, and g of x, g of x and y is 2x plus y. So remember, the constraint, you sometimes have to rewrite it so that you have all the variables on one side and a number on the other. This problem was already stated so that the variables were on one side and the number was on the other. So your g is going to be that variable side of the equation.
All right.
So in Lagrange multipliers, we take the gradient of f and we set it equal to lambda times the gradient of g. So the gradient of f is, first of all, the derivative with respect to x, which is 5 plus y, and then the derivative with respect to y, which is just plain old x. And that's going to equal lambda times the gradient of g. The derivative of g with respect to x is 2, and the derivative with respect to y is 1. So if I distribute this lambda and then set the components equal, I get that 5 plus y is equal to 2 lambda, and x is equal to lambda.
I missed something. Where did you get the lambda times the vector 2, 1 from?
That's this part here. That's the lambda times gradient of g. So the gradient of g was the derivative of this with respect to x and then with respect to y.
I got it.
Cool. So what I'm noticing from this is that it's easy to solve for x and y in terms of lambda. So this looks like y equals 2 lambda minus 5. And down here, x is lambda. Now notice that this is only 2 equations, but there are 3 variables. Remember that your last equation is always your constraint. Here the constraint is 2x plus y equals 3. So I can, in the first 2 equations, I can solve for x and y in terms of lambda, and then I can substitute both of those into the constraint, and then that'll allow me to solve for lambda. So let's say I'm going to plug in lambda for x, and I'm going to plug in 2 lambda minus 5 for y. So that's 2 lambda plus 2 lambda minus y minus 5 is equal to 3. So 2 lambda and 2 lambda is 4 lambda, minus 5 is 3. So it looks like the only solution I get here is lambda equals 2. And then I'm going to take that lambda equals 2 and plug it up here in order to figure out what x and y are.
Can you explain the constraint part again?
The constraint was given to us. So it said, find the maximum subject to this constraint. It didn't say, it didn't use the word constraint, but it said, it did imply that we were restricted to being on the line 2x plus y equals 3.
Oh, okay. That makes sense.
So usually there's, in Lagrange multiplier questions, there's going to be kind of an open-ended question. So there's going to be a function of 2 or 3 variables that you're trying to make as large or small as possible. And then there's going to be some other equation that you're restricted to. So here, it's not just going to be an open-ended function like 5x plus xy. It's going to be something like 5x plus xy equals 10. So when you have a function equals to a number, that's your constraint. So now let's plug back in. X is equal to lambda, so that means that x is 2. And y is 2 lambda minus 5, so that means that y is negative 1. So that's going to be the location of the extreme value. And then to find the value, I need to plug back into f. So f of 2, negative 1 is 5 times x, which is 10, plus x times y. So minus 2, which is 8. So the extreme value is 8, and it happens at the point 2, negative 1. Does that make sense?
Yeah, I was just confusing it up with like the grade of G and just like what to do with lambda practically.
So the examples that I posted on YouTube were kind of hairy. You might have, if you watched it, you saw there's case 1, case 1A, case 1B. And in general, Lagrange multiplier problems can be pretty bad. But the ones that you're going to see on the test are not going to be terrible. They're just going to make sure that, well, there's only going to be one Lagrange multiplier problem. And it's mostly to see that you know how to go through the process. I'm going to try to make it so that the algebra is not too terrible.
Will it be to this problem?
Not necessarily this one in particular, but you should expect it to look similar to either a homework problem or something that's on the review sheet.
Okay, thank you.
Or maybe like this, but it's not going to be just the same with the numbers changed. What else you guys got?
Are you going to have all worked out solutions to this review posted, like you did in some of the previous exam reviews?
Ask that again, please.
So in some of the previous exam reviews, you actually had like a PDF on Blackboard that showed all the worked out solutions, just like you do with the class notes and everything. Are you going to do have you done something like that for this exam review?
I haven't. I don't have these problems worked out. I just have the answers for them. But one thing I'd be willing to do is to give you guys permission to post your solutions to the discussion board. So if anybody checks their answers and sees that they match what I've posted here, then you guys right now officially have my permission to post those to the discussion board so that other people can see it.
Have we worked out number 4 from the bonus point?
We have not, and that'd be a great one to look at. So let me clear this. Let's look at number 4. So on this one, we're given a surface, 3xy plus z squared equals 15. And we're asked to find a normal vector and an equation for the tangent plane, specifically at the point 1, 2, 3. The main fact that we're going to be using here is that the gradient is perpendicular to level surfaces. So if I can write the equation for the surface in the form of a level surface, then the gradient of the function on the left is going to be perpendicular to that surface. So notice here that the surface is already written in the form f of x, y, and z equals a constant. So in some problems you need to, it might have said 15 minus z squared and you have to move the z squared over to the left. But here, notice that all the variables are on the left side already. So if I want to find my perpendicular vector, I can just take the gradient of f. So first of all, I take the derivative of f with respect to x, which is 3y. Then I take the derivative with respect to y, which is 3x. And then finally, I take the derivative with respect to z, which is 2z. Now this gives you a perpendicular vector or a normal vector at any point on the surface. If I want one specifically at the point P, then I'll take the gradient and I'll plug P in. Which means that I have to plug in 1 for x, 2 for y, and 3 for z. So y is 2, so that's 6 here. X is 1, that gives me 3, and z equals 3. So 6, 3, 6 is going to be a normal vector to the surface. So this is a normal vector. But also I can use any other vector which is perpendicular or which is parallel to this guy. So if I wanted to divide out that common factor of 3, I could also use n equals 2, 1, 2.
And
So that's going to be,
oh,
either
sorry.
one of these would be good.
Okay.
You don't need
And
to
then for
say
part,
n equal,
beg your pardon?
you don't need to say n equals 3 times the vector 2, 1, 2. It can just be the vector 2, 1, 2.
It could be the vector 2, 1, 2. It could also be the vector 20, 10, 20. Any non-zero scalar multiple of this is going to be perpendicular to the surface. Does that make sense?
Yep.
Yeah, if you have a normal vector and you double its length, then that's still going to be a normal vector. So I'm going to use 2, 1, 2 since it has no common factors. It'll be easier to work with. By the way, this was the answer to part A, or this one. For part B, I'm going to use the formula that a plane has an equation that looks like a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0, where a, b, c are the components of your normal vector, and x naught, y naught, z naught are the coordinates of your point. So I have 2 times x minus 1 plus 1 times y minus 2 plus 2 times z minus 3 equals 0. So that's 2x plus y plus 2z minus 2 minus 4 minus 6 is minus 10. I think we get 10 out. Does that make sense?
Yes.
Yeah. I feel like this question, the language of this question is really intimidating if you don't know what you're doing, but if you do know what you're doing, that is a very simple question to answer.
It is. But the main point on that question, the main reason that I give it to you, is to make sure that you remember that gradient vectors are perpendicular to level curves and perpendicular to level surfaces. I'm sorry,
So,
Mahina, I noticed that you raised your hand. Did you have a question?
Yeah, is there a way you can kind of explain number 8?
Oh, I'm so sad, Maheen. I actually just did 8 a few minutes ago, but after the session's over, I think it takes about an hour to process, but I'm making a recording of the study session, and I'll post it, and you'll be able to see it then. Does that make sense?
Okay, thank
Yeah,
you.
I'm going to set up a new YouTube playlist, and you'll just have to fast forward through it until you can find problem number 8.
Okay.
Have you
Carmela?
worked out question number 5?
I haven't done number 5. Carmela, what was your question?
So just one quick thing for the equals 15. Do we just ignore the 15, like for the final answer for part B?
Yes, the only thing that 15 has to do is that's the value of the function if you plug in 1, 2, 3.
Oh,
So
okay.
if you wanted to verify that this point was actually on the surface, you'd plug in 1 for x, 2 for y, and 3 for z, and that would give you 6 plus 9, which is indeed 15.
Okay. That's all. Thank you.
Cool. So Tanya, you're asking about number 5?
Yes.
Cool. Let's look at that one. So in 5, we're trying to integrate a function along a curve. So let me capture the important part, and then we'll do it. The curve is the parabola y equals 4 minus x squared between 0, 4, and 2, 0. And we want to find the integral along C of x cubed plus xy ds. So notice with notation, this is little scalar ds. So to find this one, we're going to be using the formula ds is the magnitude of sigma prime of t dt. So we'll have to parameterize the curve and then substitute it into this formula. And that's what we'll be plugging in for the ds right here. So let's start off with the parameterization. Since the function is, let me say it again, since the curve is given as the graph of a function, in other words, we can solve for y in terms of x, we can parameterize by setting x equal to t, and then substitute that in to get y. Y will be 4 minus t squared. So sigma of t is equal to t for x and 4 minus t squared for y. Let's figure out the bounds on t. If I want to start off at 0, 4, then notice that since x is t, that means that t would have to equal 0. And if I want to end at 2, 0, then that would mean that t had to equal 2. And we can check real quick. If we plug in 0, we get 0, 4, which is good. And if we plug in 2, we get 2, 0. So this is looking good. So now let's calculate ds. ds is the magnitude of sigma prime of t dt. The derivative of sigma is going to be 1, negative 2t. And the magnitude of that vector will be the square root of 1 squared plus negative 2t squared. Does that look okay for ds? Take that as a yes. So now let's see what our integral looks like. We're going to be integrating with respect to t, and we saw that the bounds for t were 0 to 2. So this becomes the integral from 0 to 2. And in here, I have to take x cubed plus xy. And here are the values of x and y. So x cubed plus xy will be t cubed plus x times y is t times 4 minus t squared. And then ds we found was the square root of 1 plus 4t squared dt. Does everybody see where I'm getting all these numbers from, all these variables?
I do.
Yes.
Yes.
This is the ds, and over here where it says that x cubed plus xy, you just use whatever x and y were in the parameterization. And now a little miracle happens.
Do you have like a pointer of some kind? Because when you'll say something like over here is your ds.
Can
but
you
on
not
this screen,
see the cursor when I'm moving it around? I do
yeah,
have
no,
a,
we have no, I have no cursor, so I can't see what you're pointing at.
okay.
Oh, there it is. There it is.
Yeah, I see it. I see it now.
You see the little finger as well as the cursor, or just the,
Yeah, we could not see that earlier, or at least I couldn't.
okay. Yeah, I can try to make sure that you see that in the future. So now let's simplify. Inside here, I have a t cubed plus 4t minus t cubed. So notice that t cubes cancel, and I just end up with a 4t. So everything here simplifies to 4t. And then that's multiplied by the square root of 1 plus 4t squared dt. Thanks for letting me know that, Jason. I thought that y'all could see the cursor on my screen. So this we're going to integrate using a u substitution. I'll let u equal 1 plus 4t squared. So du is equal to 8t dt. And notice that I almost have that. I've got a 4t dt. So to get 8t, I can just multiply by 2 and divide by 2. on, baby. Sorry, my stylus is ignoring me for the moment. Oh, my stylus is mad at me. Now, let me do this with my trackpad for a moment. So 2 times 4t is 8t. dt is, oh, now it's paying attention to me again. Sorry about all the scribbling. It's writing all the stuff that I had been writing before while it was ignoring me. So this is 8t dt. That's my du. And the square root of 1 plus 4t squared is the same as the square root of u. Now, as far as the bounds go, notice that when t is 0, u is equal to 1. And when t is equal to 2, u is 1 plus 4t squared, which is 17. So this ends up being 1/2 the integral from 1 to 17 of u to the half du. Now the integral of u to the half is u to the 3/2 times 2/3. And I'm going to be taking that from u equals 1 to u equals 17. 1/2 times 2/3 is 1/3. And then plugging in, I get 1/3 of 17 to the 3/2 minus 1 to the 3/2, which is 1/3 of 17 root 17 minus 1. So that's the way that I'd work out number 5. Does that make sense, Tanya?
Yes.
Cool. Sorry about all the scribbling.
Well, so I have a question. We had a cleaning crew just show up like an hour early, and I had to step out of the room for a minute, so I missed a step here. You have that one right there where you're pointing to. It looks like you did an e to the u to the 1/2, and
No,
I understand everything.
This is totally a scribble, but in Blackboard Collaborate, the erase tool erases the whole screen.
Oh.
So I can't go back and erase individual pieces, unfortunately.
So where did you come up with the u to the 1/2 du? That's like, so u is you're going with the u as the part under the radical.
The 8t dt was my du, and the square root of 1 plus 4t squared was my u to the half.
Okay, I see it. I got it.
Mahim?
Okay, so I got the snapshot for question 8 that you solved earlier. This is like a totally different question than the one mentioned on the exam review. And your answer is 8. I checked the review sheet and the answer should be 3, so I think that's like an entirely different question.
Oh, you're talking about the review sheet, not the relay?
I'm talking about the review sheet, yeah.
Oh, I'm sorry. I thought you were talking about the relay. Hold on. I don't have the review sheet pulled up, but I can. Sorry about that. I misunderstood you. Let's see. Dropbox. Oh, this is the one where I'm asking you to find the derivative of w with respect to y?
Yes.
Using the chain rule? Awesome. Let me copy that down real quick since it's on a different screen. So w is a function of r and s. R is equal to xy plus yz squared. S is sine y plus e to the xz. And I want to find dw dy at negative 1, 0, 0, given that dw dr at 0, 1 is 2, and dw ds at 0, 1 is 5. Cool. Come on. Okay. So we know that W is a function of R and S. We know that R is given by xy plus yz squared. S is given by sine of y plus e to the xz. And we also know that the derivative of W with respect to R at 1, 0 is equal to 2, and the derivative of W with respect to S, at 0, 1, 0, 1. Derivative of W with respect to S at 0, 1 is equal to 5. Cool. And we're asked to find dw dy at negative 1, 0, 0. So first of all, let's just use the chain rule. dw dy, since W is a function of R and S, and we're trying to find the derivative of W with respect to Y, if we do our dependency diagram, W is a function of R and S, and R and S are each functions of Y. So the derivative of W with respect to Y will be the derivative of W with respect to R times dr dy plus the derivative of W with respect to S times ds dy. Also notice that when x, y, and z are equal to negative 1, 0, 0, that R, which is xy plus yz squared, xy plus yz squared, that'll be equal to 0. And S is sine y plus e to the xz, that'll be sine of 0, which is 0, plus e to the 0, which is 1. So when x, y, and z are negative 1, 0, 0, then R and S are 0 and 1. So this is going to be the derivative of W with respect to R. I'm just going to use my other notation here. Plus, times the derivative of R with respect to Y. The derivative of R with respect to Y is x plus z squared. Plus the derivative of W with respect to S. Oh, I can write that as dW. I feel like I'm trying to write wearing beer goggles or something. This is dW with respect to S times ds dy, and the derivative of S with respect to Y is cosine Y. And now let's evaluate this at -1, 0, 0. Well, when I plug in -1, 0, 0 into dWdr, remember R is 0 and S is 1. So that'll be dWdr at 0, 1 times x plus z squared. Well, x is -1 and z squared is 0. So that'll be times -1 plus dw ds. Again, r is equal to 0 and s is 1 times cosine of y, but y is 0 and cosine of 0 is 1. Now it's given that dw dr at 0, 1 is 2, so this is 2 times -1, and dw ds is given to equal 5, so that's 5 times 1, and -2 plus 5 is 3. And I think that's what you told me the answer was, Maheen, isn't that right?
Yeah, that's it. Thank you.
What else do you guys have? We still got about 30 minutes left.
Have we gone over number 7 from the bonus point?
We talked about it in general, but we didn't actually solve it. So I think it'd be great for us to go ahead and go through the whole problem. So number 7 is on the fundamental theorem of line integrals. And when you run into a problem like this, it's really kind of important to read the whole problem through, because if you know that you're going to be using the fundamental theorem of line integrals, then that means that there's going to be a relatively easy way to do it, as opposed to number 6, where you're just going to have to grind through the whole thing. So let's write down what the vector field is, and also write down what the curve is. So the vector field is 2y squared minus 4x, comma 4xy plus 8y plus 5. And we're also given that the curve we're working on, I used an R here instead of a sigma. R of t is t plus 1 comma t squared, where t goes from 1 to 2. Okay, let's just save that for a while. We're not going to need it for a bit. Now in part A, we're asked to verify that f is conservative and find a potential function. So remember, for vector fields in 2 dimensions, we call the components m and n, and the test to see whether the vector field is conservative is you check whether the derivative of m with respect to y is equal to the derivative of n with respect to x. So let's check that. The derivative of m with respect to y is 4y, and the derivative of n with respect to x is 4y. Oops. So that means that it is conservative. If this had been a 3-dimensional vector field, you'd have had to check that the curl of f was equal to 0. So now let's see if we can find a potential function. Remember, a potential function is going to be a function f so that the gradient of the function f is equal to the vector field f. So that means that the derivative of the function f with respect to x has to equal m, and the derivative of function f with respect to y has to equal n. So df dx in this case would have to equal 2y squared minus 4x, and the derivative of f with respect to y would have to equal 4xy plus 8y plus 5. So let's integrate. The first one I'm going to integrate with respect to x, and that will give me 2xy squared minus 2x squared. But here, instead of writing plus c, I'm just going to make a note that I could have an entire function of y sitting over here, because if I differentiated a function of y with respect to x, that would all equal 0. So there could be one or more terms involving y's and constants missing right here. For the second one, I'm going to integrate with respect to y. Working my way across, the integral of 4xy with respect to y would be 2xy squared plus the integral of 8y with respect to y is 4y squared, and the integral of 5 with respect to y is 5y. But here, instead of plus c, I'll just make a note that I could have terms involving x's over here. So let's see what must be in our potential function f of x and y. I've got to have a 2xy squared. So that takes care of those. I have to have a negative 2x squared. So that takes care of this guy. I have to have a 4y squared. And I also have to have a 5y.
How come you haven't really carried out the full integrals to see what those y's and x's are? Like usually when the book does these, it'll show what those are, and then you can decide if you need them or not.
I may have done it in a different way from the book, but I have. Let me grab the pointer. Notice here that on this side, I have that f is 2xy squared minus 2x squared plus terms involving y.
Mm-hmm.
The terms involving y are right here. They're
Okay.
4y squared plus 5y. And over here, I know that I have some missing terms of x. Here it is right here. The missing term of x involving x is negative 2x squared.
Okay.
So they're in there, but I think I'm doing it just slightly differently. So that's the end of part A. Part A is to check its conservative, which we did, and to find the potential function. Now for part B, we'll use the fundamental theorem of line integrals, which says that the integral of f dotted with ds is equal to the potential function at the terminal point, which I've been calling q, minus the potential function at the initial point, which I'm calling p. So p, the initial point, is going to be r of 1, because we started off with t equals 1. So I'm going to plug 1 into my parameterization. That gives me 2, 1. So that's my p. And q is my terminal point, which is r of 2. And plugging 2 into my parameterization, I get 3, 4. So f of q minus f of p will be the function over to the left, evaluated at 3, 4, minus that same function evaluated at 2, 1. And I think it'll just be frustrating for me to try to do the arithmetic for you. But according to my notes, according to the answers that I posted, you want to get 157 if you go through and do the arithmetic. Does that make sense, Carmela?
The last part, no, because somehow I got 4, but
You got 4 where?
For the FQ minus FP?
Were you substituting into this function over here?
I don't think so. I think I literally just did 3 minus 2 and then 4 minus 1.
Yeah, then that's what it is. So you'll have to take that 3 comma 4 and plug it into this. So it'll be 2
Okay.
times 3 times 4 squared minus 2 times 3 squared and all of that.
Okay. Thank you.
Yeah, it'll be a bit of a mess, but it's just arithmetic.
Okay, thank you.
Before we leave number 7, does anybody else have questions about this one that we just did?
I kind of do. Just looking at it where you're doing your fundamental theorem. So it's f of q minus f of p, and how do you why do you know that p is r1 and q is r? I mean, I get that those are the endpoints, the terminal initial, but how would you know to put the 1 and 2 into your r function and then put that into your f function rather than just say subbing? Like, I might have made the mistake, I might have subbed 1 in for x and 2 in for y or something like that into the original f. I don't know, it's just like understanding which functions get used and what gets subbed into what.
Well, remember that your parameterization is giving you a curve in the plane where the x coordinate of a point on the curve is given by t plus 1, and the y coordinate is given by this. So it wouldn't make sense to plug in the 1 or the 2 for x and y, because this is a t value. This is a time. It's not a point in the plane. And this function is evaluated at points in the plane. So the way that you get from a particular time value to a point in the plane is by substituting into the parameterization. So remember, the parameterization is like saying x equals t plus 1 and y equals t squared. And your function is expecting x's and y's, not t's.
Gotcha.
Now, another way that this problem could be stated on the test is it could just say that C is a curve from, I'm going to stop writing it. It could just say that C is a curve from the point 2, 1 to the point 3, 4, and it might not even give you a parameterization. Or it could say that C is the line segment from 2, 1 to 3, 4. All that matters is that you have enough information to figure out what the 2 endpoints are of C.
Got it.
Thank you.
Oh, y'all have other questions on either the relay or the review sheet? Something that some of you might not have heard if you weren't in the room yet is if anybody feels like they've gotten problems correct on the relay and you want to post it to the discussion board, feel free to. I'll be looking at the discussion board somewhere or sometime, either this evening or tomorrow morning at 10, and I'll look to make sure that the answers look correct. If they're not, then I'll post a note letting you know where you guys went astray. But at this point, feel free to post solutions to this to the discussion board.
Are we gonna have questions like number 3 on the relay on the test where it's like they give us curl of the gradient of f and we have to say whether it's like a vector, scalar,
Or nonsense?
yeah.
You're not going to have that on this test, but that was just kind of to make you really super aware. For example, if you take the curl of a vector field, you better be writing a vector as your answer. Or if you take the divergence of a vector field, you better be writing a scalar as your answer. Because when folks first learn this stuff, occasionally I'll find people taking divergence and writing a vector down. So that was just kind of training your eye so that if you saw a curl, you know that you're going to be writing a vector field as the answer. But you're not going to have a problem exactly like that. You're not going to have a problem like that on the test. Fair question.
Thank you.
Do you have time to work 10?
Let's see. That's kind of long, but we certainly have time to start it. Does anybody else have a quicker question? It's a good one to spend time on because there's one like that on the test. Okay, I'm going to take that as let's do it. Actually, if you'll will excuse me for just 1 second, I need to respond to something, and I'll be right back to you. Hang on just 1 second. This isn't what I'm responding to, but just kind of maybe interesting to you. One of the guys that I run with, for some reason, decided to take a cruise to Peru, and he is now trapped in Peru. It wasn't a cruise, it was a tour, and the tour company has abandoned him and like 200 or 300 people there. So I'm getting zillions of texts and emails asking us to contact our senators and see if they can try to get him back out or get the group of Americans out. Anyway, side note, now let's look at problem number 10. We want to find the absolute extrema of this function. F of x and y is equal to 2 plus 2x plus 6y minus x squared minus y squared on the region that is on your relay sheet. I'll label that a little bit better. I'm not going to write down all the conditions. I'll let you refer to the sheet, and I'll get write them down as we go along. So remember, what we need to do is find the interior critical points, we need to find the boundary critical points, and we need to identify the vertices. So let's start off by looking at the interior critical points. We find those by setting the gradient of the function equal to 0. So taking the gradient of this function, we first differentiate with respect to x, which gives us 2 minus 2x. And then we differentiate with respect to y, which is 6 minus 2y. And we set that equal to the 0 vector. So we're setting that equal to 0, 0. So 2 minus 2x is 0, and 6 minus 2y is 0. So that's looking like x equals 1 and y equals 3. And I gave you a kind of helpful graph. It's fairly easy to see in the graph that that point 1, 3 really is on the interior of that region. In some of the problems we got, we found more than one interior critical point or possible interior critical point, and maybe one was inside the region and one was outside the region. But here we just got one and it was inside the region. So we're going to take that and add it to the list. So we'll start the list over here, although we'll probably run out of space. So in terms of interior critical points, we would be adding 1, 3 to the list. Next, we start looking at the boundaries. And there are 3. Let's call them C1, C2, and C3. C1 is going to be the slanted line, which is y equals x. C2 is the horizontal line, y equals 4. And C3 is the vertical line. It's the y-axis, so x equals 0. In the picture here, I directed those line segments. That's really not necessary. That's not the kind of problem we're doing. We're not doing an integration problem here, so that it's not important to give an orientation. So let's start with C1, y equals x. So to begin with, we parameterize. So we can let x equal to t, and then y also equals t. So sigma 1 is equal to t, comma, t. And then we substitute that into our function. So f of sigma of 1 of t is equal to 2 plus 2t plus 6t minus t squared minus another t squared. So that looks like 2 plus 8t minus 2t squared. And then we take the derivative of that and set it equal to 0. So the derivative is equal to 8 minus 4t. We set that equal to 0. And that gives us t equals 2. So this is kind of like what you're asking about earlier, Jason. So t equals 2 gives us the time that we have a critical point. But if we want to find out what that point is in the xy plane, we have to substitute back into the parameterization. So sigma 1 of t is t comma t. So the point xy is 2, 2. And we add that to the list. So sigma of 2 is 2, 2.
Oh, it's like 1, 2.
No, it's meant to be 2 comma 2. Okay, that was C1. C2 was the curve y equals 4. So when I parameterize, y's got to equal 4. So x equals t. I'm parameterizing a horizontal line segment, so y is constant and x varies. So sigma 2 of t is equal to t comma 4. I'm going to get parameterization and plug it into f. F of sigma 2 of t. I'm putting t for x, so that's 2 plus 2t plus 6 times 4 is 24 minus t squared minus 4 squared. Let's see what that gives us. 2 plus 24 minus 16 is 10 plus 2t minus t squared. And I'm going to take the derivative of that and set it equal to 0. So I take the derivative, which is 2 minus 2t, set it equal to 0, and that gives me t equals 1. So once again, I take that t equals 1 and plug it back into my parameterization over here. So that'll give me the point 1 comma 4. And as I go along, I should be making sure that all of these points are actually on the parts of the segments that I care about. And if you look at the diagram, that point 2, 2 is actually the midpoint of curve C1, and the point 1 comma 4 is about at this location along curve C2. So everything's going great so far. Unfortunately, I can't erase this screen without erasing all of it. So I'm going to squeeze down here for C3.
I mean, I'm screenshotting as you go along, so.
For C3, let's see, that's a vertical segment and the x coordinate is 0. So let me skip directly to sigma notation. Sigma 3 of t, the x component is 0 and the y component is t. So f of sigma 3 of t, I'm going to put in 0 for x and t for y. So that's 2 plus 0 plus 6t minus 0 minus t squared. So if I take the derivative and set it equal to 0, I'm going to get 6 minus 2t equals 0. So t equals 3. And plugging that t equals 3 back into the parameterization sigma 3, I get 0, 3. So the point 1, 3 was my interior critical point, and the points 2, 2, 1, 4, and 0, 3 are my boundary critical points. And then finally, I have to add on to the list my 3 vertices, which are 0, 0, 4, 4, and 0, 4. And at this point, you just take all of these numbers, plug them into the original function, and then we have to pick up the largest and the smallest values. So I don't know whether we really want to go through all of that. I can plug one of them in. If I plug in 1, 3, I get 2 plus 2 plus 18 is 22 minus 10 is 12. So it looks like if I plug in 1, 3, I'm getting 12. And if you go through and plug all of them in, then according to my answer sheet, you should find out this is actually the absolute minimum. All the rest of these values end up being bigger. At 0, 0, you should get 2. And at 4, 4, you also get 2. Oh, sorry, this is the max. 12 is the maximum value. And these turn out to be the minimum. Jason, I'm getting feedback from your microphone. So without plugging in the other values, does this give you an idea of how this problem works out?
Totally.
Yeah. So first you find interior points, boundaries, and then the vertices.
That's right, Diego. And usually the longest section is finding the boundaries because there's usually at least 3 boundary curves. I can't specifically remember the problem on the test right now, but most likely it has 3 boundary curves. Okay. The one mistake that I sometimes see people making is they parameterize. So let me use the pointer. So for example here, they'll parameterize, they'll do that correctly. They substitute into f correctly, but sometimes they set that equal to 0 before they take the derivative. So remember, since you're trying to find a max or a minimum, you want to take a derivative and set the derivative equal to 0. So for each boundary curve, parameterize, substitute, take the derivative and set it equal to 0 and solve for t. Once you get your t, you plug it back into the parameterization and that gives you your point. So what else you got? We've got just a couple minutes left. Are there any others that you need hints on?
I don't know if the review has one, but finding a normal vector to the level plane, I think it was.
Yeah, Diego, you might have missed it, but a little bit earlier in this video, we did a problem like number 4 on the relay sheet.
Is it like the same process? Because I did that one.
Yeah. So if it's a tangent plane, then you do it that way. If it's a normal vector, the only difference is you use the formula p plus tv to parameterize a normal line. So for a normal line, it's p plus tv, and if it's a tangent plane, it's that a times x minus x naught, and so forth.
Okay.
So I'm going to be posting some advice on the test later, and I think that you already have a list of what the questions are going to look like. I think I put a description of the test on Blackboard. But just kind of to forewarn you, it is going to have 3 max-min problems, and one of them is going to be absolute extrema, like this problem number 10 that's on screen. One's going to be relative extrema, where you have to find the critical points and then apply the Hessian test. That's usually a lot faster than 10. And then one of them is going to be Lagrange multipliers. And that's not necessarily going to be that hard. I'm going to try to make it so that the algebra is not terrible for you, but it sometimes slows folks down. And those 3 problems, I forget, but they're worth a fair amount each. I tell you how much if you look on Blackboard. And they're the last 3 questions. So make sure that when you're taking the test, you leave plenty of time to do those last 3 questions, because they're worth a bunch of points. You got a question, Thomas?
Yeah, so just right quick, I've been searching through all kinds of apps for the Android to try to find something, and I'm not gonna lie, a lot of them you have to pay for, and not looking to do that. So would it be okay if I just took a bunch of pictures, put it on a Microsoft, and then convert it to PDF from there?
Thomas,
Sure.
did you look at Adobe Scan? Because that's free.
Adobe Scan?
Yeah, that's an app for the Android that I use.
Okay. All right. Well, I'll check it out. If that works, then I'll use that. Then if not, then the Microsoft thing is okay.
Yeah. One thing I'd recommend doing is you are probably going to be turning in homework sometime later today. Try it, whatever method you want to use on test day, try it out on the homework just to make sure it works. And after you submit it, see if you can look back at it and make sure that what you see is clear.
Okay. All right. Sounds good.
Yeah, I'm making kind of a big deal about the PDF just so that I can hopefully clearly see it and also be able to grade it online.
Yeah.
When I get a Word document or like a picture, I don't know that the markup tools work in Blackboard as well as they do for PDFs.
My concern with the PDF is that, like, even though it uses my cell phone camera to take a picture and convert it automatically to a PDF, it's not as sharp and clear as if I just use my camera to take a photo of the page. So that's the only thing I'm a little worried about, is the way it'll look to you.
The problem with that, Jason, is sometimes when you sent me photos of your homework, they get cropped in weird ways.
Yeah.
So sometimes it's like the picture, which would look normal on your screen, gets blown up, and I only see like the center third of the picture instead of seeing all of it.
Mm-hmm.
So
No,
that
I'll try
might
the
be
PDF.
what I'm using to read it.
It should be, because when I email the whole picture, you definitely get the email attachment is the whole picture, but whatever you use to open it or print it or read it is cutting it off. But I'll try the PDF. I'm just worried it won't be as sharp and crisp as a camera picture.
Yeah, but something I will recommend to everybody is to take a look at the picture after you upload it, or just do a trial run with either the homework or maybe with the relay that you already uploaded, and make sure that what you uploaded is clear. One student used a free version of some app, and it came out like heavily watermarked, like it had all kinds of little lines across it, proprietary lines, and it made it super hard to read. So try it out with the homework and whatever, something low stakes, so that when it comes to test day, you can do it smoothly and you know that I'm going to be able to read it. John, I see that you came into the room. What did you use to scan yours? Because yours came out good.
I use Scanner Pro, but you have to pay for it.
Never mind.
It works really well. I use it a lot, so I didn't mind paying for it. I mean, it's really helpful to have just for any course that I've been taking so far.
So let me see. Diego, yours also came out clear. I took a look at yours.
Yeah, my iPhone just comes with like its Notes app, just has a scanner.
Yeah, on iPhone, I hadn't used it with Notes, but Scannable is one that works on iOS, and it works great.
Oh yeah, that one too. I use that one too.
On Notes, does it automatically put it into one file, or did you have to compile?
Yeah, I had to compile it, so I just like took multiple pictures, sent them to my computer, and then from there on, I made a single document.
You might try Scannable, because it must be free, because I usually don't pay for apps. And with Scannable, you can just take one picture after another, and it automatically puts them into one file.
Okay.
I don't know whether you want to try something out right before the test, but if you have some time to test it, it works great for me. Does anybody else have recommendations for an Android app? Adobe Scan, I hear, is a good one. No suggestions. If you come up with something, post it to the Blackboard or to the discussion board, so other folks will know. People have been coming in at different times. Something I do want to let you know is that I'm recording this session, and I hear that it takes Blackboard Collaborate an hour or so to process it. But once it's processed, I will post it to Blackboard. I'll probably create a new YouTube playlist and send you guys a link to it. So if you want to scan back through it for any questions that other people asked, you'll have that available hopefully in a couple of hours, a little bit later this afternoon. Looks like it's about 1 o'clock. Any other words of wisdom I can give you before we end the session?
You have another one tomorrow, right?
Yeah. Yesterday when I had my session for usually Cal 1 on Monday, Wednesday, I only had 2 folks show up, and I was able to answer their questions in about 40 minutes. So if you guys come in tomorrow, then at least to begin with, I'm going to prioritize the Cal 1 questions, but there just were not that many people showing up yesterday.
No, because I have physics from 10 to 11:30, and then I think I'm supposed to do physics lab from 11:45 to 1:10 or something like that. Completely confused.
That doesn't leave a lot of gap in the middle.
Anyway.
You guys use the, feel free to use the discussion board too. One of my Cal 1 classes already is getting pretty active on the discussion board. They're asking each other questions and also asking me questions. And between 10 and 11, I'm going to do what I can to address any questions that pop up there.
All right, thanks, Professor.
Okay. It feels like this is winding down. Paul?
Cancel that.
I don't know about the viral activity on that. I don't know what you guys noticed, but I'm labeling all of the videos as being for kids. Hopefully that means that you're not getting any weird watch it next videos coming up after it. I think that also means that you can't add comments. So if you have comments, you're going to have to send them to me directly. Okay, guys, thanks for coming in. Please let others know. I know that there are some group chats out there. If you are chatting with other people in the class, let them know that there will be a session, or this session will be posted to YouTube sometime later this afternoon. And good luck studying. Remember that the homework is due by midnight tonight.
Thank you. Bye.
Okay, ciao, guys.